So, disco lights part 2, eh? This is the other one, the bigger one. This one was basically dead. We tried to put some power into it via the light bulb in case there was a short anywhere, and the bulb didn't even try to light up. So we can say this one's dead like the other one was originally. So the first thing I guess with this is going to figure out how to actually get into it. Camera was a bit I don't know if it was flickering. I could see the flickering on the screen. I'm assuming this is the way in. That can be sometimes a challenge, you know, with stuff, is figuring out how to actually get into it, but this is not going to be one of those problems. So, well, there's some stuff in there, isn't there? I mean, compared with the other one, there's some shit in that one, isn't there? Ha! Look at that. Right, let's see if we can. What we got on there? There's the display and panel. That's what we have here. This is power coming in to here. We have a fuse. I can see that. Yeah, this one quite different from the other one. You remember the other one, we had a power supply which gave us 12 volts, and then the 12 volts went to a controller which had FETs which turned each channel on and off. What we have here is something quite different. So we have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. We have here effectively 4 power supplies. I'm thinking either, yeah, it's a 4 colour: white, blue, green, red. So I'm guessing that's going down to the LEDs. I mean, it's going that way. So that looks like that's the 4 colours. What was it? Red, green, blue, and the other one's ground return. Let's see. Yeah, unless there's another wire going somewhere else, which I don't see. This looks like it might be a red, green, blue, and maybe the 4th power supply is to power up the circuitry. Not sure. So I guess we have to have a look to see what we actually have in here. Let's see if we can take this apart a little bit further. Circuit board's held on by screws. I can see. Can I see a cooling fan down here? Not sure. Power supply is held on by screws. This one goes to the front panel. Shall we take it apart, or shall we have a look to see what first? I think we'll see what's what first. We can check if there's power coming in. The fuse looks intact. This looks a little bit flaky. This is a okay. Can you see that on the camera? I'm not sure if you can. Down here, there's something broken up. Yeah. I'm sorry if that's not focusing very well for you. This is probably a thermistor, so this is kind of like to stop an inrush of current. So it's like a temperature sensitive resistor, and it being probably the sieves with the power coming in, and this is in bits. So visibly straight away we can see there's a problem with this. So I think what we'll do is we'll disconnect this circuit board, and we'll have a look around and see what we really have here. So we know this is power coming in, so we can disconnect that one. Let's find the screwdriver. Oh, a bit tight that one. Yeah, I've got it. So we can disconnect the power coming in. This is just ground. This is going to the controller, I'm guessing, down inside there. Or maybe it's just the front display. It's held in with, let's see if we get to the view. It's held in with glue, so that's a bit of a pain. So we need to just crack that glue first. Normally for this I use like a soldering tool. It's like a little blade, it's almost like a knife really. And I'll see whether I can get this down inside here. Yeah, and effectively break the seal where the glue is. I might have it. No, it's still well stuck. Let's turn it around so I can actually see what I'm doing. See the front of it. So, yeah, I've got the knife down the side there now. So there we go. It'll come off. So obviously, when we put this back together, we need to remember to put a bit of glue on there. I'm assuming that's because these are like portable. You know, they moved around them on the road, so they put the glue there to stop them falling off the connectors. What else do we have down in here? Where's my other screwdriver? This is a ground connection, so we can disconnect that one. Let's put the screw safe. I can see down in here there was a little washer that's fell off. So, oops, a little washer, so we'll keep that safe. And then this lot here is going to go down to the LEDs. So I think we'll just make a note first of the colours there, or even simpler, just make a note. That's old technology, eh? That's old hat. Let's just take a photograph. That's take a photograph of the thing. We can see though. Okay. Always worth doing stuff like that, because you'll be surprised how many times you can't remember what went where. So we have that. This is coming off. So these we can now take off here. And just try and position that. I can pretty much imagine how this works. So what you've got is you've got a power supply, a switch mode power supply, controlling each colour. It's possible one of them, this one here, might be just powering up the circuitry, because I think the idea is it switches these power supplies on, and they can go from 0 volt up to, you know, the maximum voltage for the LED. It'll be a constant current supply. That's what LEDs use. But if all the LEDs are off, all these will be off. So then there's no power for anything else. So I wouldn't be surprised if that one is a power supply that supplies the controller, and maybe this is RGB, not RGBW, red, green, blue, white. But you see in this channel, you know, with me, a lot of this is like best guess. You have a look at something, and then as you go along, you might modify your opinion of what you've seen. You know, so don't expect to have it right every time, and certainly be prepared to change your mind. So that's that lot. This is where it's burnt out, I can see that. So we should be able to get the circuit board off now. What's it held on with? Screw. One here. I can see the fuse is intact, so the fuse hasn't blown. But that whatever down there, that's obviously blown up. Sorry, that bumpy here. I'm wearing a headset with a microphone. I don't have just a mic, so it's got headphones and a microphone. And when I lean over, I'm actually banging my head on desk cam. That's what it is. So when you hear that bump, it's not me sneezing or something. It's just me hitting the headphones against that. At least I'm not hitting my head, I guess. I'm just hitting the headphones against it. But I'm sure the noise that makes is quite annoying. I'll do it again, you see. Okay. One circuit board. Thought I could see a fan under there. So this lot will go down into the LEDs which are down there, yeah? This small one, this is obviously the connection for the fan. And that leaves 4 red, green, blue, white. So now I think we can say with a lot of certainty here, we have 3 colours, red, green, blue, and the other one's the return. If it's anything like that Chinese thing we looked at before, the wires will be mixed up. In other words, you know, the colour of the wire won't match the colour of the LED. But, you know, that's what we had last time, who knows. So, that bit, for now, can go out of the way. Let's just stick that down on the floor. We don't need that. You had something fall over then, didn't you? So this is the PCB. Here we have the bit of something that's broke off, okay? Burnt out, blown up. And that comes from here. If you look down the side of here, so this is your power coming in. And here, let's see if you can see it. I'll get under the microscope if you like. Here, this is where something burnt out. Then, we have, remember the other one, bridge rectifier. So power comes in here through the fuse. These capacitors are just to stop effectively spikes, noise going back up the mains wiring, cause interference, and that coil as well. So basically the live will come, or live or neutral, whichever one of them will come through the fuse, through this side of this coil, to this bridge rectifier. The other one will come probably through this thing that's burnt out, through the coil, to the other bridge rectifier input. And these capacitors are just connected directly across live and neutral. If you watched the video on the previous one, you'll remember the bridge rectifier was actually 4 diodes, individual diodes connected up. This is actually the same thing, but it's just encapsulated in one. Let me show you what a bridge rectifier is. So I'll just find a bit of paper, get everything on the bench. Okay, that's my light bulb circuit. See, I didn't even find a fresh bit of paper. So let's have a look what a bridge rectifier actually is. This is your power coming in. This is live, this is neutral, and this is alternating current, yeah? So this is 0 volts, and you can see it first goes positive, negative, positive, negative. So effectively the current's doing this, it's alternating both ways, yeah? Like this. And we need direct currents to power this sort of circuit. Almost everything, apart from electric motors and a few things, use direct current. So the bridge rectifier works like this. We have a diode from here to here, okay? And then we have another diode like this from there to there. That's from your live. Again, we go from the other end. So we have a diode same way as that one from there, yeah, and these two join together, and we have another diode same way as this one, so the opposite way, and that goes to there. Here and here. This is your DC. So how this works, imagine this is, let's say this is the live, yeah. So this is like a 0 crossing point, so the waveform comes up. So this live goes more and more positive, yeah? The waveform's going up like this. And while the waveform's going up, the current passes through this diode. These diodes, basically positive, negative, they always pass current in the direction of the arrow. See the arrow in the symbol, yeah? So while this is going positive like this, the current's flowing down here. When this is going negative, like this, the current goes down that one, the opposite way, yeah? So this here is your plus and this is your minus. So during the positive half cycle, your live is connecting to here, yeah? During the negative half cycle, it's connecting to there, so that's how you get plus and minus. Now look at your neutral. This is also doing this as well, yeah? So on this one, during the positive half cycle, yeah, in the direction of the arrow goes to there. So whichever one of these is positive goes to there, plus, yeah. During the negative half cycle, it goes the opposite way through that diode and round here to there. So when both of these are negative, it's there. So what you actually get here, effectively, if you were to measure from there to there, instead of seeing that, that's the AC, what you'll see is this, you'll see positive, positive, positive. So that's your zero crossing, yeah? Not to scale. So effectively this is 50 hertz, yeah? So this will go 50 times a second, it'll do that, yeah? This basically is 100 hertz because it's taken the bottom off and stuck it up there. Bump, 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 bump. And for each one of these cycles you get 2, yeah? So effectively this is like 100 hertz, you could say. And that's what it's doing. So now we've got all positive. This is 0 volt level. But it's bump, 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 bump. So we need to smooth that. So what we do is here, we put a capacitor. And this capacitor charges up to the peak voltage of this here. If that's 220 volts coming in, that's the average root mean square. The peak of this is probably about 350 volts. So this capacitor would hold about 350 volts. And when this voltage effect comes to 0, this continues to supply the circuit, the load, yeah? This is your load, LED lights, whatever you want to power, that's your load, yeah? So that's what you see. So if you just put an oscilloscope on here, you'd see this without the capacitor. With the capacitor, you'll just see DC, 350 volts. This is 0 volts. So that's what a bridge rectifier is. And the last one we saw was made up of 4 individual diodes. This one is just 4 individual diodes in a package, and it's got 4 legs, yeah? And this has 4 legs. Look, AC, yeah, AC, plus, minus, okay? And those 4 legs is what this will have. And it's back to front, so you can't see them. But you'll have coming into here, I would probably say, without getting a test meter, on the middle 2 is the AC coming in, and then one of these will be, yeah, it is because the capacitor's here, yeah. Negative of the capacitor goes to here, so that's the negative of the bridge rectifier. The positive end of the capacitor is here, positive end of the bridge rectifier. And that's basically what you have. And from this to then, positive, it goes to this one, goes to this one, it goes to this one, and it goes to this one. And these are your supplies. So these 4 are all power supplies, switch mode power supplies. Each one's got its own input capacitor. Remember, it was on that other one, we just had one input capacitor. It has its own controller. It has its own transformer, primary and secondary. Do you remember the other one? Little capacitors. These are almost certainly part of the startup circuit for each of these. There's little diodes down here. These will almost certainly be from one of this. This has 2 secondaries. One secondary powers that after the initial startup, which is this capacitor, and the secondary goes to the output, yeah? These things will be diodes, rectifier diodes, so these are output capacitors, rectifier diodes, and then your power comes out. And we've got red, green, blue, and then the 4th one is going to be powering the control circuit. So that's what we have. That's what we see. That's what I see. And I'm hoping to teach you, so that's what you see. What else did we have on the other one? Yeah. We had, do you remember it? We had opto isolators. So effectively, on this side, the high voltage side, this controls the driver, yeah? This is your power IC that drives that transformer. So that there, it sends a signal back to here to tell it wider pulses or narrower pulses. That's how it alters the voltage, yeah? This side will monitor the output voltage of here. But there'll be more to this. There'll also be a control signal coming to each one of these from the controller board, and that's how it dims or brightens. It changes the. It tells it what voltage it wants for the brightness of the LED, and this here, and there's one between each one. There's one. We can see them. So there's one here. There's another one down in there. There's one down in there. There's one down in there. So the controller IC is driven from the logic board, the power IC rather, from the logic board. The logic board will tell that how much voltage to put out, and this opto isolator will tell it when it's reached the right voltage. So that's the feedback. That's how that works. It's 4 power supplies. So what's wrong with it? Well, what's wrong with it is down here. Something burnt out. Let's just get under the microscope, so you can see what it is. This might be difficult because of the thickness of the board, but let's have a look, see if we can actually do this or not. I say the thickness of the board is because I probably can't lift it up, the microscope high enough to focus on it when I turn it upside down. But let's have a look. My microscope camera's frozen again. I don't know what's going on with this. Let's see if I can actually free it up. Normally I just click on this thing. You might not be able to see this, I can see it. I deactivate the camera, I reactivate the camera, it comes back on, and it's working. Yeah. So there you can see what burnt out, and by it says NTC. Okay. And I'll tell you what this is. It's got a funny little symbol. That symbol is a thermistor. A thermistor is a resistor, but the value of the resistor varies depending on temperature. This is negative temperature coefficient. So that means this: as the resistor gets warmer, the value becomes lower. You also get positive temperature coefficient, which is the opposite way around. So when you first plug this in, this will start off at a relative high value, 100 ohms or whatever. I mean, whatever value. But I'd imagine it's somewhere in the region of 100 ohms or tens of ohms. And current will pass through it, and the current is going to go into the bridge rectifier and into this big capacitor, which you probably can't see very well under the microscope. You can see it there though, yeah? Okay. Now, what you have when you start off, this big capacitor is completely discharged. So you get what's called an inrush current, where when you first plug this in, there's a huge inrush of current through the fuse. The fuse will be a slow blow, so it can handle that for a few milliseconds without blowing. It'll probably tell you somewhere. No, I can't see, but okay, that's where it'll be. No, it's a fast blow. I can see F. Fair enough. Is it 5 amp? We can look at it. But anyway, the fuse is designed so it can withstand this inrush of current. It only lasts like probably less than a second or something like that. So this starts off at a relatively high value, and it limits the amount of current that comes in to the capacitor. That's why the fuse doesn't blow. Is it? Confusing myself. It doesn't blow on the inrush because this limits the inrush. If this wasn't there, yeah, the fuse would probably blow. So this starts off at a high value and power sort of trickles into it. But because it's a resistor at high value and there's current flowing, it gets hot. It starts to warm up, and the more it warms up, the lower the value it gets and the more current it can pass, which means it warms up even more, and so on and so on. So after, it might take a second. This is now a relatively low value resistor because it's hot, and this capacitor is charged. And what this was, it's blown up. I mean, it's blown up, simple as that. And here, there, that's what's left of it. So, apart from saying we know it's a thermistor, we don't really know what value it is, yeah? That's one reason. Now, why is it blown up? Okay, we don't know the value, but why is it blown up? Well, it's blown up because too much current came in, basically. So it just got so hot it exploded. Why did too much current come in? Well, too much current came in possibly because there's a short circuit somewhere. So before we think of sticking another thermistor in there, and I suspect if that's the case, basically this blew up before the fuse could blow up. That's why the fuse hasn't blown. It looks intact. Looks good. In fact, can you see? Yeah, I'm sure you can see down here. This blackened area. That's like effectively the blast of the explosion when that thing blew up. So that's blown up with quite some force. So definitely we're going to have to figure out why that's happened. Okay. No point sticking another one in unless we know why, because quite likely it'll just blow up again. Plus, at the moment, I don't actually know what value that thermistor is. I'm not sure how critical it is either. and we'll have to see if we can find that out somehow. But anyway, that's what's gone on there. So let's go back over to the main camera again for now, and just make this bigger again so we can see it. Right, there we are. So what's blown up? Well, we know what's blown up. Why is it blown up? First reason is probably somewhere as a short circuit, and that short circuit could be in one of several places. So we're not even going to try and power this thing up. We're going to try and figure out where the short is. So we'll go on to ohms range, test the meter, and let's have a look at the circuitry coming in. So we know pretty much, yeah, from here, okay, live or neutral to the fuse, through this coil, and it will go to this bridge rectifier, what it should do, on one of the two innermost, I think. Can't see it at the moment, so maybe there's a fault there. Okay, let's have a look. So we have this is our fuse here, yeah, power in, fuse. So from here to the coil, other side of the coil, and that goes to this side of the bridge rectifier, yeah. Other power comes in here through the thermistor, which is no more. So obviously there's no power. This is one end of the thermistor, and that's the other end. But the thermistor's gone, literally. Yeah, it's gone. So other side of the thermistor to the coil, other side of the coil to the other input of the bridge rectifier. So that's how. And then from the other side of here, you've got plus and minus, which go to the capacitor. This end's minus. We can see the minus sign. So the first place we're going to check for short is here. Okay, there's no short circuit there. So it doesn't have a direct short circuit on the mains, but there could still be a short circuit. You'll see down in here it's dirty. I've seen cases where effectively that becomes conductive and shorts out, but when that happens you get like a blast radius like you have from that other thing that's blown up. So I don't think that's the case. But we can have a quick look. Where did these things go to? These are the controller chips, 1, 2, 3, 4, yeah? And let's have a look to see what these controller chips actually are. Not easy if we get this under the microscope for you, so you'll have to let me just read it. So the first one says OMO. Let me actually look through the magnifier myself without. I need a longer wire on this headphones, is the truth of it. Let me have a look at myself through the. Yeah. Looks like DM 0565R. DM 0565R. So let's go and see if we can find that one. How do we set this to screen capture? Yep. Let's have a look for it. DM 0565R. Datasheet. Okay, yeah, that's the thing. Handful of legs on it. So to all datasheet and see what this is. That other disco light, by the way, those FETs, those A0, whatever the number was now, I managed to get 50 of those, including postage, to Gran Canaria for €1.86, less than €2 for 50. So why buy one? You know, let's have 50 of them. We can fix that thing, and it looks like a very useful FET to have. I mean, often we can use an equivalent, you know. So probably a lot of times when we want a FET that can handle 30 volts, 6 amps, and now I've got 50 of them on the way. So this is the thing. This is the data sheet. There we are. Fairchild DM 0565R. green mode Fairchild power switch. And we can look at it. Well, there's our bridge rectifier, which I've just spent 5 minutes drawing, and it's very clearly shown this here. So, as we said, AC in, when this end is positive, the voltage flows up through this one and charges the capacitor. When this end is positive, it flows up through this one and charges the capacitor. And the same applies when this is negative. When it's negative, it flows down through here to the negative end of the capacitor, and this one, when it's negative, flows that way, negative end. That's what I just spent 5 minutes drawing. I didn't really need to, did I? So, what this thing is, basically, you know, we've looked before at these controllers, and they have a MOSFET, or 2 MOSFETs. This is all just built in one, basically. And it's very simple. So, VSTR, this will be startup voltage, yeah? And in this case, I can tell you that is probably, no, just connected straight to the okay, but that's your VSTR. That's your startup voltage. So on this one, that just connects straight into the positive end of the bridge rectifier, yeah? And that's probably VSTR. Let's have a look. Let's be sure. I'm sure that's what it is. Let's just get on the data sheet. VSTR. This pin is connected directly to the high voltage DC link. At startup, the internal high voltage current source supplies internal BIOS and charges the external capacitor via that's connected to the VCC pin. Once this reaches 12 volts, the internal current source is disabled. Right. So what that's telling us is that when this is first switched on, this is like a high value resistor that charges this capacitor. If you remember the power supply, I mentioned there was like a 2 meg resistor. That's internal on this. This charges up to 12 volts. Once this reaches 12 volts, that internally is disabled, yeah? So there's 12 volts on VCC. This is the power for this controller. This starts sending pulses, pulse, 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 down here, yeah, and switching this FET on, off, on, off, on, off. When the FET's on, switch is on. Look, straight from your 350 volts through the primary, straight down, the FET's on, and straight down to negative. So there's your circuit. Through the FET, sorry, from the positive, through the coil, through the FET, down to negative. When it switches, so that's when it switches on, yeah? And basically, this magnetizes. It only stays switched on for like a microsecond or even less. You know, it depends on the frequency of this thing, but microseconds or less, yeah? Then this switches that off. When this switches off, what happens is here, the magnetic field in this coil has to collapse, and when it collapses, the power has to go somewhere. And what happens is, this end of the coil effectively becomes positive. So the power can't flow through this, it's off, so it goes back through this capacitor, this resistor, and the power circulates like that. So this is discharging the magnetic field, yeah? And that charge discharge over and over again is what drives the secondary. This is your secondary, this is your power rectifier diode capacity, yeah? This is your, we talked about them, this is your opto isolator. It has the Zener diode, resistor, and it's connected across the output. And the idea of this is, this Zener diode is like a switch in a way. We'll talk about the components, but what this does is, it's like a diode, but it effectively, it's back to front. You see it's wired in the reverse polarity to a normal diode. If it was like a normal diode, that would be like the arrow pointing downwards to conduct you. But when this reaches whatever voltage, this is probably, that diode LED probably is 2 volts, so this is probably set to about 10 volts. So effectively, when you get 10 volts across here, this switches on. And it powers the LED. The LED lights up. And you can't see it, it's inside the opto isolator. And that light shines on this transistor, which turns it on, and that's your voltage feedback. Yeah? So when this reaches working voltage, this turns on, and that tells it you're up to voltage now. When the voltage goes a bit below, this turns off, and that says it's a bit below now. And if you look at this pin here, VFP, sorry, this pin internally connected to the inverting input of the pulse width modulator. This is a comparer. So what they're saying is that the voltage that's on here basically controls the width of the pulses, yeah? It also mentions that it should have a capacitor on it, and that if the voltage on this pin goes to 6, then overload protection is activated and it shuts down. So not only that can that pin be used as a feedback, which it is here, it can also be used as a shutdown, which it's not here, but it says it can be. Okay, so that's that. Voltage start, capacitor charge up to 12 volt, this starts switch. And it said, once that reaches 12 volt, this disables. It's no longer supplying power into this capacitor. So this capacitor starts to discharge. This is a load. It's driving this controller here, and the voltage starts to drop. It'll be designed so when it drops to a certain amount, let's say 8 volts, whatever the number. When it drops down to 8, this will switch back off. But it's pulsing this. This is driving here, and it's producing voltage out here. There's another secondary here, look, and this one, via a rectifier diode, starts charging up the same capacitor that was charging. So this charges up to 12, this starts going, this drops a little bit, this kicks in and charges us back up to 12, and this keeps running. You see that? So that's effectively how it works. This supply is only to get it started, and this supply is to keep it running. This is quite a nice setup, because the whole idea of this is that this turns on once and this starts running. If there's something wrong over here, like say there's a short circuit on this doesn't get any voltage, or it doesn't get very much voltage, so it can't charge this capacitor back up, and after a very short time this will just discharge the capacitor, it'll switch off. And now, depending on the chip, it'll either switch off and then this will activate and charge back up to 12, and it'll come back on and have another go, and continually it'll try. And if you hear a power supply that's making a chit 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 sort of chirping noise, that's what you're hearing. You're hearing this continually trying to drive this, yeah. Other ones, it'll try once and it'll just shut off, and until you disconnect the power and plug it back in, it won't try again. So probably just spent too long talking about that circuit, but I hope, again, I'm trying to show you what you'll see in real life, and you can understand a bit about, hopefully you may even understand what all those parts are doing. I've been through them. If not, go into the comments on here and say, Rich, this wasn't clear, and we'll do another video. We'll do more videos on those anyway. So that's what we see there. So let's now go back to our device. Screen capture off. There we go. Oh, what didn't I do? I didn't make a note of the pin numbers. Okay. I was that busy talking, I didn't even make a note of the pin numbers on the device. Right, let's just go back to screen capture once more. There it is. So there's 5 pins, yeah? And somewhere in here it's going to tell us which one is which. This sort of shows you what's internally in there. But to us, it's just a black box. We're not a circuit designer. We just want to know what pin is what. So, we have, I'll make a note of these and then you can see it. Pin 1 is drain. This is the high voltage FET drain. So this is what it is designed to drive the transformer directly. So that connects to the transformer, yeah? Ground. This is the control ground on the other side of this FET. So that's pin 2. Ground. VCC. This is the one we were talking about, whereby it gets the startup voltage, switching the thing on, and then it goes on to say that once it reaches 12 volt, the internal high current source is disabled, and the power is supplied from the auxiliary transformer winding. That's that secondary I was showing you. That said takes over, yeah. So that one is VCC, and we know that needs to be 12 volts for the thing to switch on. So we'll make a note of that. 4 is voltage feedback. And we do know with this one, it does mention, goes to the optocoupler, and if we have more than 6 volts on this pin, the thing will shut off. So we'll make a note of that. And this one, VSTR, high voltage link. It starts up. Yeah. This is the one that effectively powers it up initially. Yeah, that's 6 voltage startup, and 5. There's no connection. Maybe the pin isn't even there. And this shows us a little diagram of how it is. So we can also, I'll just draw that. 3, 4, 5. 5 pins. 1, 2, 3, 4, 5. Okay, I've drawn that as well. Oh no, there's 6 pins. 1, 2, 3, 4, 5, 6. And I've made a drawing of that thing. Okay. So now we can go back to the desk cam and we can go back to our unit and we can have a look to see if we can figure out what is or isn't working correctly on this. Where are we now? Desk camera on, off there. Okay guys. So, still reusing the same bit of paper. This is a picture of the device. So the hole there, that's can you see? That's this hole here, yeah. And it's shown as that sort of it's shown as sort of this way up. So we know pin 1 drain. That's the one that goes to the transformer. Pin 2 is ground. 3 is VCC. That's the power to this thing itself. 4 is the feedback and 5 is the 6 is the startup. But the ones we're interested in first is really 1 and 2, yeah. So we can have a quick look here. In fact, you see, there's a cutout here. This is like a cutting into the circuit board. That one's got dirt in it. That's not good. This is because there's a high voltage on this going to the coil, and this is this cutout so that you don't get sparks or even like conduction through the plastic of the circuit board. They're clogged up and dust. I mean, as long as that dust isn't conductive, that's not a problem. But I've seen it happen. So let's just clear the crap out of them while we're at it. Eh? So where are we? From the big capacitor over here, positive as this one. I can look. There's a negative. So positive is this one. It's the red wire on that one. And this is going to go via the coil to probably pin 1 on these. Yeah, pin 1, pin 1, pin 1. So that's your power coming in. Pin 2 is the other end of the coil, which goes to ground. Sorry, the other end of the FET, which goes to ground. So we can also look at that as well. This is the negative end of the capacitor. And again, pin 2. Yeah, it's this one. Connecting via a 1.5 ohm resistor. That'll be a little low value resistor in circuit. And what that's doing basically is I'm going to show you very quickly what it's doing because this is interesting. Let's just go back to the screen again. Let's go back to this. In fact, we can see it there. What we have here is basically from here to ground we have a low value resistor about 1 ohm. Now the current flowing down through here when this switch is on also goes to that resistor, and it'll develop a voltage drop across the resistor, and almost certainly this circuit will be measuring that voltage somewhere. But you probably going back, we'll go back into the feedback one way or another. Be measuring that voltage, and that's over current. You often see this. It's a current sensing resistor, so that little bit of voltage drop there actually senses the current. And you'll see current sense resistors a lot, and sometimes they go open circuit and stop things from working. That's why I thought it was worth mentioning that one. Well, yeah. So we got those coming in. We know there's no short circuit across any of these because otherwise the short circuit would be across there, and there isn't a short. So there's no shorts on this side. Let's have a look at the other side of the circuit. So these are your transformers, and on the output side, let's see where the inputs are. I found the pins. Yeah, this is your input of your transformer here in here. There's 4 wires. So one wire will be the secondary that powers back into the controller. There's a big gap down here. Yeah, you'll find this on power supplies. It separates the high voltage side from the low voltage side. This side is isolated and it's safe. All this is at high voltage and it's not safe. Not even the ground here is ground. The ground is what's called hot ground, which basically You remember that bridge rectifier? Right. And I said the negative end, when live it is negative, it connects to there, and when the neutral is negative to here, yeah? So half the time live's connecting to here, and half the time neutral's connecting to here on each half of the cycle. And the same with the positive. So this ground isn't ground. It's actually like, they used to call this half mains potential. What they really mean is all of the mains potential for half of the time. So every half cycle, for half a cycle, live will get connected to here, and then neutral, live, neutral, and the same here. So none of this is safe to touch, yeah? Unless you have an isolation transformer, which we can come to. But just bear that in mind, that ground here, the negative end of this capacitor, it's ground for this circuit, but it's hot ground. And half the time, that is actually live. And the other half of the time, this side of it's live, yeah? These things can be dangerous if you don't understand them. That's why I'm stressing this over and over. Sorry, yeah, I'm repeating myself, but it's important. So, that's the high voltage side, and we can't see any shorts across the capacitor. I just checked all these chips, but I know the way it's wired, so I knew there wouldn't be any shorts. So the other possibility is we've got a short on the output side, and if we've got a short on the output side, almost certainly it'll be one of these rectifier diodes. But first, let's have a look if we've got a short on the output side. So this is one of the outputs to red. Okay, there's no short there. This is output to green, there's no short there. Output to blue, there's no short there. Output to white, there's no short there. So I can't see any short circuits on the output. These diodes down here will have either 2 or 3 legs. Yeah, they've got 3, I can see them. The reason they'll have 3 legs is because it's like a it's a diode network. I'll draw it for you in a moment. Let's just check these diodes, okay? Go to diode range, yeah? Yep, 0.53, 0.610, and these two won't read anything particularly. Next one, 0.53, 0.61, yeah. This one, oh, I'm reading the wrong way around. You see with these diodes, if you read in one direction, you get a reading, yeah? If you read the opposite direction, you get nothing. That's because the diode conducts one way and doesn't conduct the other way, yeah? Oops, I'm off the camera, sorry. So, one way round, we can see 2 diodes there. Other way round, you see nothing because they only conduct one way. And the same on all of them, yeah? I don't think this camera focuses very well, does it? Okay. Just go to the last one. Each of these is a double diode. But how that basically is, how much can we fit on this bit of paper now, yeah? Now let's have a fresh bit of paper so we can see what we do with that. That's already well scribbled on. Yeah, so these diodes with 3 legs on. Yeah. And that's like where the screw bolts and fastens it to the heatsink. Yeah, you see them down there with 3 legs and screw, yeah. Okay, but you can see it now. So what these things are basically, they're 2 diodes in one package, and they can be common anode or common cathode. So depending which type they are, you have to find the data sheet. What you've either got is you've basically got 2 diodes connecting like this. Yeah, or you've got 2 diodes connecting the other way. Yeah, and quite often they can be used in parallel. So you'll sometimes see where basically that both these 2 are connecting together, and they go into one end of your coil, and your other end is going to ground. And this is coming out, this is going, this is your positive. From here you've got a big capacitor to ground. So you'll quite often see that sort of thing. So finding these diodes with 3 legs on, they're diodes. Okay. You can look up the part number. I mean, there's no harm in doing that. A bit hard to see, but if we looked up the part number of that diode and went onto the data sheet, I'm sure we'd find out exactly what it is. So let's have a quick look. But I don't think there's any shorts on this at all. All the diodes look okay. They're testing okay. I can't see any shorts on the output. So I think the next thing with this is instead of replacing this thermistor, because I don't know exactly what it is, I'm just going to short it out. I'm just going to connect a bit of wire across that for now, and connect it to my power supply via the light bulb, which also will stop any insurge of current, and we can have a look to see if it works. Because as things stand at the moment, I don't really see any reason why that thermistor is blown. In other words, I don't see a short circuit. It could be that something's breaking down when there's a high voltage on it. I've seen that before. So you don't see a short circuit on your meter, but when you turn it on, you certainly do. Because something goes pop, or fizzes, or whatever it wants to do. So let's get rid of these two legs, which is the remainder of that thermistor. And nice, let's just, for now, we'll short it out. If the thing works, okay, we need a thermistor, and we'll get one. But we don't have to sort of try and find a thermistor just to test this. You know, we can test it, especially using that light bulb in series, because that affects itself as a surge suppressor. It will stop the inrush of current. That's what this thermistor was designed to do. This is quite a good technique. You just bang and it should fall out. Of course it didn't. That one did. This one's been stubborn. Okay. Oh. I'm just trying to show you some trick. That's one that just fell out. The other one, tweezers on it. That's out. So that's the remains of the thermistor, and you can see that's been. Can you see that? That's been well cremated, yeah. It's possible it just failed, you know. It just, you know, sometimes components sort of get just effectively seem to get tired and they just give up. I've seen fuses that just go. They don't like blast and go all blackened inside. They just go open circuit. I've seen that many a time. Just trying to get a bit of solder out the holes here. We'll often find by adding a bit more solder helps you to remove the solder. Add a bit more solder, add a bit more flux, yeah? And now let's just see if we can clean that off. Bit of solder braid. Okay, that's not wanting to come clean. Let's use the desoldering needles. I showed you these if you watched the tools and equipment video. Let's no, that's that was my jeweler's loop. Where have I put? Where have I put my desoldering needles? Here they are. Everything on your workbench should have a place that it lives. You know, everything should have its home, and it should always be at home. If you do that, every time you want something, you just know instinctively where to grab, yeah? Of course, some things like the jeweler's loop and the desoldering needles and the flux and, you know, those things, they just live together. But you're not like trying to hunt around there. So like, I don't know if you see me doing this, but basically I'm just pushing the needle through the hole, yeah? This last one is actually managed a bit of solder stuck to it so it won't come out. There you go. So that's our hole. These were the desoldering needles, just little stainless steel needles in different sizes. They live in this little box, and then they live over there with the flux and a few soldering and that sort of stuff, the braid. Okay. So that's that lot there. So what we're going to do is now we're just going to short this out. I'll tell you what we'll use. Do you remember, if you saw the last video, I was using a couple of these old resistors, effectively just to poke down the end of a connector to measure voltage, yeah? So let's just stick one end in there and solder this, and just cut it off. Got these at an electronics fair years ago. Some guy come to the end of the day and just put a huge box of old components on the bench, his desk. He'd gone home and he just put a sign on saying, "Free to a good home." As you can imagine, there was like a load of guys there. Has to be the guys, don't it? Those sort of things. There's a bunch of guys there just grabbing handfuls of this stuff and sticking them in bags. And there was the women that belongs among weird, isn't it? There's the women that would accompany some of the guys just standing there and gas thinking, oh my god, what's he taking home with him now? But it's free, but it's free. But where are you going to put it? Go and put it back where you found it. That's what my mum used to tell me. Go and put it back where you found it. Okay, so we've shorted out the thing there. So we need to test it, don't we? And how easy is that going to be to do? Let's have a look. Move the meter. Tidy up the bench, first. Tidy up the bench. Keep your workspace tidy. Don't leave a mess about the place. Richard, don't break your own rules that you're trying to get other people to follow. I'm moving stuff you can't even see, but the bench is coming tidy. How about there we go. Even for now, the voltmeter is going to go off and go back where it lives. Everything has a home in this workshop. Everything has a home. Stick that there. 2 scrap bits of paper. Bin. Okay. Well, say scrap bits of paper. That's the stuff I was trying to teach you. Okay. Right, let's have a look at this now. Let's see if we can connect this up safely while it's on the bench, and see if we can actually figure out what's happening. So, controller on there. Now I'll do that last. These are coming from the LEDs, yeah. Remember, I took a photograph. Now you're going to find out exactly why I took a photograph, because I've already forgotten which one goes where. Okay. Yeah. You see why I do these things? Red, green, blue, white. Okay. I've developed a lot of these things I'm doing. I've just developed this over many years of like making mistakes and doing stupid things. Gradually figured out how to avoid doing those stupid things, and this is why I work in this kind of like fairly rigid plan, if you like, way of working. But it works for me. Phone's gone off, don't need that anymore anyway. Slipping out red. That's the other red. Oh, that's interesting. I've got a feeling, you know, this is 4 colours now, and it looks like each one of these, and I just assumed there were like 2 wires effectively feeding each colour together, and they're not. There's a plus and minus. Unfortunately it says, I bet some of you have been screaming out at the screen while you've been watching this video saying, but Rich, there's 2 wires to each LED. Yeah, you're right, there is. So it is 4 colours. I wonder where the control circuit gets its power from, because presumably at some point all these are switched off when there's nothing on the LEDs, unless it kind of like goes to like a voltage that's lower than the LEDs need to turn on. But I doubt that. Unless there's some other way the controller gets its voltage from this. That does beg a question though, you know. I was looking for shorts before with all this like disconnected. What if I've got a short on one of these LEDs that I'm now reconnecting? So basically before we move the camera so you can see more of what I'm doing. There we go. Okay. They're all marked underneath, by the way. I told you that, you can see now. And they say positive and negative, and I'm pretty confident, I'm sort of guessing in a way, that the one with the black stripe is a negative. But you remember I said to you, with the LEDs, it doesn't really matter if you connect them the wrong way around. The worst things happen is they just don't light up. This is hard to just get the wire to clip in that. Has that got it this time? No. These things work backwards. Yeah, because the other ones fell out as well. See, how does this actually work? So, oh, I see. I think there's like a place above the. There's like a little metal thing in there. I think this has to go. Does it go above there? Should it? Yeah, yeah, it does. Look, oh, that's the green one. I'm assuming, as I say, I'm assuming that the black one is a negative end of the LED, but if I put them on back to front, it won't do anything bad. It just won't light up if they're the wrong way around. So look at the photo on here again, see if we can see any of the black stripes. Eh? So oh yeah, look, we can now. So yeah, so I can see the black stripes. See how fortunate that was. I took a photograph of that. Yeah, I can see it's red, red, black, green, green, black, and so on, and white, 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 very clear. So the red goes to the end, nearest this fan connector, and working on from there. So nearest the fan connector, this is the red, this is red, black. I'm not deliberately doing this, by the way, just to prove what I'm trying to tell you. This is real, you know, and this is showing me and showing you why what I'm saying, why what I'm telling you is the way to work. Green, not green. Yeah, green black. This is green black. This one's green. You have to get them above the slot. There's like a little insert in here, and they have to effectively go above the insert, otherwise it doesn't grip them. Just loosen this one off. And there we are. Get it in above the thing. Probably help if I held it the other way up. Actually, yeah, there. Let gravity is my friend. Yeah. You know, gravity was invented by Isaac Newton, and it's chiefly noticeable in the autumn when the apples are falling off the trees. So they say. Blue, black. White. That's in. So it's possible if there's a short circuit on one of these LED strings, that could have caused that NTC to blow. I don't think it's very likely, but certainly in the realms of possibility. Okay, that's on there. Let's just check again, just to make sure. I can't see you have like a whole row of short circuit LEDs, but I can certainly see like you have a wire going down through here and it's touching the metalwork or something stupid that's happened. White. No, nothing there, no shorts here. I could get the bench power supply actually and I could test these, but don't really need to. No shorts there. This one's the fan. This one's the controller. Yeah, let's see if we can get us into here. Right. Sorry, I keep realising I'm going off camera. Goes in there, so that's all connected up in a rather precarious manner, but it's connected up. Power's coming in. Yeah, let's have that one as well. Yes, it's unplugged. Doesn't really matter which is live and neutral. It's all AC to me. Let's connect those. So we've shorted out the thermistor, and we can just check that now. So we can go meter Where can you see it? Yeah. Test your leads because it just fell out. So neutral in this case comes in and goes to the bridge rectifier. The live comes in and goes to the bridge rectifier. So we've shorted out that thermistor, which is not a permanent solution to this, you know, because probably the fuse will blow if you keep on switching this on and off. Now bang my head on the lamp. So that's that there, yeah. I guess what we're interested in now is to see, does it work? So we will plug it in, and we're going to connect this to the mains via a light bulb, as I was doing before. Let's see. So we plugged in. You can't see the light bulb. That's a nuisance, isn't it? But you'll certainly see if it works, and you'll certainly see if something goes bang. Let's get you a nice view of that. Yeah, there you go, a nice view of that. Okay, so we're going to switch this on, and we're going to double check we are on. Yes, we are on the light bulb, limiting the power, and we're going to switch it on, and we're going to see what happens to this now. It's working, and the light bulb's flashing. The light bulb's flashing because it's drawing more power than 60 watts. Let me see if we can see. You see my light bulb here, yeah? Yeah. So basically it's trying to draw power, and as it draws power, it's drawing more than 60 watts. So it was flashing on and off the LEDs. So let's just switch that directly to mains, no more light bulb. And it's on. Red, blue, yellow, green, white. Can you see that? So we fixed that one, apart from the fact we need a thermistor. Let me see if I have, do I have any? I don't know. The other option is just to give the guy this thing back and tell him, look, it might blow the fuse if you keep using it on. It won't, if it's running, it'll be fine. It's like when you first switch it on, there's a possibility of blowing the fuse. While I then order a thermistor. So yeah, let me have a look. I'll go into my stock of bits and bobs. Just give me a second. Let's see what we have. Okay, one moment. Yeah, we do have. Just get into the drawer of bits. Right, so yeah, we have some thermistors. Move all that away from it. We have a bag of them. Problem is, we don't really know what the original one was, but we can take a guess. You know, we can stick one of these in and see what happens. The first thing we need to figure out is whether these thermistors are a positive or negative temperature coefficient. So it wanted NTC, wasn't it? It said by its NTC, negative temperature coefficients. So basically that means the resistance goes lower as it warms up. Well, there's an NTC. It says NTC on it. Oh, I've got quite a few of these NTC. Yeah, one says 309, 10D9, 3D9. So we don't know exactly what. That's a big bugger, isn't it? We don't know exactly what these are. We can probably look it up. Or shall I have a look? So we have NTC 3D-9. Let's see if we can see what that actually. I mean, I don't know what that is. So let's have a look. NTC 3D-9. Oh, there it is. 25 of them for €1 with free shipping. These things are cheap, aren't they? Data sheets, NTC thermistors. So I like to look on all data sheets if I can find that one. I find it's a very reliable place. If I can't, data sheet for you, let's try that. NTC 3D9, so let's see what it is. NTC 3D9. Power type thermistor, okay, that sounds positive, doesn't it? That's all blurred. That's not the screen capture. I can't actually read that. It's like the screen's gone all blurred, like a double vision. Let's find another page. I can't even. Oh, PDF. Let's try the PDF. That's a weird effect, isn't it? I can't even read it. Try another site. NTC 3D9. Spanish site, doesn't really matter. Exactly the same things happen. Something strange with my PC here. Let's just open the browser again. It's okay on this page. NTC 3D9 datasheet. I can read that now. Can I read this now? Yeah. Positive temperature coefficient thermistor. To be connected in series with a power source to avoid the surge current. That sounds good, doesn't it? At the instance the electronic circuit is turned on. The device can effectively suppress a large surge current. Resistance and power consumption can be greatly reduced after that through continuous effect of the current, so it doesn't affect the normal working. Okay, that sounds good. NTC is what it is, negative temperature coefficient. What's the 3D9? Let's see if we can see 3D9. So it's saying it's 3 ohms at 25C. Yeah, it's just a low value resistance. Then as it warms up, it goes down. Approximate resistance at maximum current. So it starts off at 3 and goes down to 0.12. That sounds good enough to me. How much? Oh yeah, like 4 amps. That's got to go in. I mean that's got to do the trick for sure. Okay, let's just go back to the camera. Desk cam. Okay. So NTC 3D9. Your little beauty, eh? These are, you can see, these are not new. These have been taken off scrap things. It's quite a nice way of getting stuff. You know, really don't throw anything away if you can't fix it or you don't want it. Just use it for bits. Take all the bits off, and don't sling them all in one big box because you'll never find anything. So this is either a bit of OCD, but really it's been organised. Stick them in a little bag. That says thermistors. Those are voltage dependent resistors, which is another type of resistor. In a little drawer that says on it, can you see that? Is that any better? Thermistors and VDRs, and that goes in my rack of drawers back here. And then when you want something, you can find it. Okay, so I've lectured you again, haven't I? Richard, you're lecturing these guys. Unplug. I'm now banging my head on everything again. 1 moment. I'm actually stuck by the microphone lead, and take the headset off. Hold on. For safety, always unplug it. I know the switch is switched off, but one of these days somebody else is going to walk and something's going to happen. The switch will fail. Yeah, that sounds unlikely, doesn't it? And all of a sudden the thing you've got in your hand becomes live. So you know, just switch it off. can we get this thing to fit in the board? Is it any good? That's the first question. Is it any good? Well, let's see if we can tell, because as I said, this has been taken off some scrap bit of equipment. Well, I think he said, what did he say? It was like 3 ohms or something at 25 degrees, and then as it gets hot, it goes down. So this should be about 3 ohms. 2.7. That's looking good, isn't it? Let's see if we can actually. Yeah, let's test this. Why not? Let's test it. We got a little bit of time, haven't we? You're not in the rush, are you guys? Let's test it. Stick that on there. Sorry, let's test it and you can see what I'm doing. Yeah. This is the thermistor. Let's have the camera up here somewhere. Go on, camera. Stay in a position where you can actually see what I'm doing, eh? Okay. Thermistor. Crocodile lead. Black. Yeah. Thermistor. Yeah. Crocodile lead, which has 2 ends. Red. 3.7 ohms. Yeah. 3.7 ohms. Now let's get the hot air and see what happens when we warm that up. Okay. Switch the hot air on. We can just reach it. It's changing. Oh, I thought they went the other way. Well, it's certainly changing. That's going, and it says it's an NTC, so, and it said on the day sheet it should go down. I don't think it's duff. I'm going to stick it in there. Maybe it has to have current passing through it rather than the temperature. Somebody who's watching this, can you explain to me why? Ow! First of all, can you explain to me why I picked up something that I knew full well was hot? And after you've explained that one, can you tell me why that went up in resistance when I put the heater on it, when I believe it should go down in resistance when I put the heater on it? But it's going in the board. What's the worst that can happen, eh? What's the worst that can happen here? Letters on a post, answers on a postcard. Okay. What's the worst that can happen? The worst that's happening is the legs won't fit through the damn holes. That's the worst that's going to happen. In the meantime, I think I might just stick this to the back end of the board, because where this board fits into this thing, there's a lot of room behind this. So if I was to tag the thermistor on the back, it's not going to be causing a problem. The holes are clean. Oh, do you know why it's not fitting through the holes? Do you know why? What did I do earlier? I sold a piece of bloody wire on to the thermistor, didn't I? So Captain Chaos strikes again, eh? It's not going to fit through the holes, is it? Because there's a bit of wire on here. That'll have a lot to do with that. Come off, bit of wire. We no longer need you. Your task is completed. You're done with. You're finished. Finito. Now we need to clean the holes out again. This is where we used the solder braid, and then we gave up with that and we used the desoldering needle. Well, let's have a go. Bit of flux. Solder braid. Bit of solder braid. Yeah, here we go. Solder braid. Try and get this a little bit higher. You can see where I am here, can't you? Cut off the used bit of braid because we don't need that. And let's just see if we can take the solder off and clean the hole this way. Close but no cigar, as they say. Go for the other one. Nope. So we're back to the needles once more. Find a nice thin one that's small enough to actually go through the hole, yeah. needle, heat. That's through. That's through. Now shall we see if our little thermistor actually fits through the holes. It's a bit fiddly down here, it's in an awkward position. But if it will go through the holes from the back, we know it will actually go through the holes. And it's worth going from the other side. Now it's very tight there. Because of where it is and because there's a lot of space behind here, I'm just going to stick it on this side. I can hardly get it through the holes from this side, and to get down that gap inside here, so you can see there's like a gap there, yeah, and to get in there is like devil's own job. So let's stick it on this side. This goes inside here, and it stands like at least an inch or more away from that cooling fan, so there's plenty of room in there. Therefore, we can bodge it. we can bodge it. We can bodge it and scram. Electronics engineers. Bodge it and scram limited. Okay. Let's whack that on there. Let's whack this one on here. Yeah, we're good. We're good. We soldered. We're in. We're there. We're done. We're balanced on the edge again. Living on the edge, eh? Living on the edge. It's clear for any crap off this desk. Yeah, it's nice and clean. The light bulb isn't in the circuit this time. I am going to plug it back in again before I switch on, because I've done enough daft things on this video. I've given all of a good laugh already, I'm sure. So yeah, we plugged in there. No light bulb in. We're just going to switch this on. Ready for the bang? Nah. So we're going to run that for a few minutes. If that thermistor doesn't commit carry, which is on the back of that board, you probably can't see it, yeah, sticking out the back there, yeah. If that doesn't burn up, then we're going to declare this one fixed. The guy can have it back, ready for the weekend. The other one, we've ordered some parts, some FETs for next to nothing. Okay, so there you are, guys. That's 2 successes today. How much do we charge for this sort of work? Normally, I mean, I'm spending a lot of time making these videos. I'd probably have that fixed and done in an hour. I wouldn't be messing around trying to work the circuit. I'd just replace the part, maybe 30 minutes. I normally charge out at, like, say, €35 for the first hour, and then generally less for the following hour. So most of the jobs I do are 35. I've done 2 today, so this guy's a regular customer, so the other one would have probably took me a little bit longer messing around, because there was 2 faults, and I was a bit daft on the first one, and missed the obvious. But yeah, I'll probably charge this guy €60–70 for the 2 repairs today, and that's probably half a day's work realistically. So if you're wondering that, yeah, you can make a bit of money off this, certainly. Okay, guys, see you on the next one.